Well, we're back here at the Cave of Science, and thought we'd try something doing the another type of review on a video here. So let's go. Sedimentary rock, if you remember from class, sedimentary rock uh, is the type of rock that's formed from loose particles, and typically sedimentary rock, much of it's laid down by ancient seas, ancient oceans, some type of water deposits. We talked about sandstone, limestone, shale, and typically that really forms the layers in sedimentary rock. What role does it play in recording the past? Fossils are in it. You don't find fossils in igneous or metamorphic rock because of the heat and pressure of the igneous or metamorphic. So fossils are definitely going to only be found in the sedimentary rock. We looked at earthquakes. Uh, you'll see on the test there's a graph something similar to this. The time travel, for instance, let's say if the the shear wave or the compression wave traveled 10 minutes, how far did it get? So we could take 10 minutes and there'd be the shear wave, drop it down about 3,000 kilometers. If it was a compression wave, 10 minutes, right about here, about 7,000 kilometers. Uh, so it's graph interpretation. We've seen many of these over the course of our study this year. If the reverse question was asked, the compression wave, how long did it take to go 8,000 miles? We'd go from the x-axis up to the curve, bring it over to the y-axis, and be about 11 minutes. So that's the type of stuff we're talking about when we're looking at for the earthquake waves. Geologic time, the time scale is based on different rock layers. The geologic time periods, pretty much the ones we had to know earlier. Quaternary, the age of mammals, is where we live. Paleozoic is where life became abundant. Precambrian is the one that takes up the vast majority of geologic time. So if you see some type of graph, you can see Precambrian here. Time is in billions of years, where if you look at this part here, this is all the top part up here. So Precambrian, about 88%. So any type of graph, whether it be a bar graph, a pie chart, or anything, the Precambrian is going to definitely take up the most space on something like that. Fossils, what are they? They're evidence of previous life forms. And again, we already discussed that they occur in sedimentary rock. Many fossils are of shells. I think Mr. Carpenter brought one in that he found, I don't think when he was camping, and it was a shell. Shells are the most likely to be found because much of the sedimentary rock was deposited by ancient seas or oceans or some type of water. The best chance to become a fossil, bones, shell, teeth, and be buried very quickly before scavengers or before they can decay due to the elements. Sedimentary rock layers. This is actually a cross-section, a part of the Grand Canyon. And as you can see here, shallow sea, streams and ponds, streams. This one was actually desert, so it's all sandstone. But you can see shallow sea, streams. And again, the vast majority of sedimentary layers were deposited by shallow seas or some type of water environment. Hint, hint. Index fossils. There's a few questions in index fossils. Again, it's a relative age dating. The characteristics of an index fossil got to be easily identified, geographically widespread, abundant, in a relatively short lifespan. And again, relatively short could still mean millions of years. A good example of this on this slide is you've got all these sedimentary rock layers. They're all shells, so it's definitely they were all deposited by a water environment. And we've got four different types of fossils here: A, B, C, and D. And the question might be which one's going to be the best index fossil? Well, relatively abundant. So that means there's got to be a fair amount of them. Relatively short lifespan. So probably a relatively short lifespan would occur in only one layer of rock, and easily identified. Well, we can identify these pretty easily just by their pictures, and widespread geographically. So ideally, we would look for a fossil that is only one layer of the rock that occurs throughout all four of these outcrops on here. So if we look at this one occurs in two layers. Not too bad here, but then it occurs in two separate layers there, so it probably uh, wouldn't work too well. This butterfly shell here occurs layer, 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 so that's not too bad, but then it occurs in two layers here. So kind of not a relatively short lifespan. We've got this some type of critter here, occurs in two layers here, occurs here, occurs again, pretty, it's widespread, but doesn't have a relatively short lifespan. And so we can look at, let's see whatever we got left in outcrop one. Got this type of shell here, just in one layer. Looking at outcrop two, it's just in one layer. 3 is in one layer, and 4 is in one layer. So it's widespread, easily identified, and a relatively short lifespan. So this one here, letter A, would make a good index fossil. So I expect to see some decoding, if you will, questions like that on the test. Radioactivity, half-life, you're going to see 3 or 4 questions on there, and most of them are going to be of the chart variety. Be able to interpret the graphs. So if we go through 2 half-lives, let's look at this one. If we bring it over to the y-axis, it looks like that's about 200. Could be 200 years, 200 days, whatever it happens to be. If it goes through 4 half-lives, looks like it's about 100. If we want to find what the half-life of this material is, if this is 2, then this is probably 1, and it looks like it's about 500. Likewise, you got to be able to do the reverse too. And again, we did many of these. Let's look at the next one here. The amount of parent is the original material. The daughter is the what the isotope is really breaking down into. So number of half-lives. Say if it went through 2 half-lives, how much is left? 1/4. Went through 1 half-life, 1/2. And again, the half-life is the amount of time, and that time is a constant it takes for something to decay into a stable isotope. So if we got the 100% here, this would be 50%, 25, and so forth. Let's just say, for instance, if this was 100 grams, after 1 half-life, what would be left? Well, if we started with 100 grams, then this would be 50, then this would be 12, or 25, excuse me, this would be 12.5, and so forth. You got to be able to interpret these things both ways. Let's say if we had a material that had a half-life of 20 years. Now that's the half-life. After 2 half-lives, how old is it? Well, if it goes through 2 half-lives and each half-life is 20, 2 times 20 is 40. It's going to be 40 years old. So again, I'd go back and review that material because there's going to be there's 3 or 4 questions on half-life on the test. Mountain building, 1 or 2 questions on mountain building. We looked at the type of faults: strike slip, thrust or reverse. That is where that hanging wall is shoved over, and then a normal. The thrust or reverse, I always kind of look, you've got a overhang, hence the term hanging wall, and it overhangs the footwall. Here on a normal, this would be the hanging wall. Well, it's not overhanging the footwall at all there. So that's a pretty good idea of those, and I would go through and review those again also. Go through and review your relative age dating principles. We did the cross sections. All those principles. Here we've got some material. Looks like some erosion. Some material was there. Again, shallow seas. Some materials deposited. Looks like we had some more material deposited. Some more material deposited. Some more material deposited. And then we had this igneous intrusion that went up all the way through. So this igneous intrusion here that went into all of these, looks like this would be the youngest. and this would be the oldest there. And you'll see one or two questions on relative dating principles. Transgressions, regressions. Uh, Again, if it's a transgression, the water is just going higher up the beach. And as you can see on here, this water is higher here than this one or this one. So this would be a transgression, to transgress or to increase or go over. This one would be a regression, as the water is decreasing, if you want to think of it like that. So that's probably the easiest way to think of those. Hydrology, we looked at seawater, read some graph interpretation. Definitely if you look at this graph, salts and seawater is chlorine, 55%. So there'll be a couple questions relating to parts of seawater there. We talked about different clines, a thermocline, a halocline, a pycnocline. Thermocline is where you have this rapid decrease in temperature, really in a relatively narrow part of the ocean. So thermocline is the temperature one. Halocline is the one for salinity, and then a pycnocline is density. Now you got to remember, for density, seawater depends upon two things for its density, and that is the amount of salt and also the temperature. And as we learned, if you put more salt in it, the greater the density of water. And again, the lower the temperature, the density of water will also increase. And so we learned about these clines. The ocean floor we looked at. We can just start with this one. Some of these you're not going to be responsible for, but you should know the mid-ocean ridge. You have the abyssal plain. This is a plain here. They call this the abyss, but consider this the abyssal plain. We have the continental slope, where it starts to reach up back to the continental shelf. So we need to know continental shelf, continental slope, abyssal plain, and then the mid-ocean ridge. Don't worry about the volcanic island arcs, a guyot, or a seamount. We're not going to worry about those on this test. You had a lecture on tides. Tides, if you look at the right picture here, tides are caused by the gravitational pull of the sun and the moon. Both of these gravitational fields influences tides. The moon much more because it's much closer. Three types of tides. I'll actually tell you right now, don't worry about mixed tides. But we'll look at a 24-hour period or one day, semi-diurnal. You have two highs and two lows. And in a diurnal, you have one high and one low. Those are the two you should worry about. Don't worry about mixed tides at all. We also looked at the breaking of waves. Now we talked about where this depth of water here is 1/2 of the wavelength, and wavelength is crest to crest or trough to trough. So if this was a 10 feet here, this water right here at this would be 5 feet deep. We talked about you'd be able to dive underneath a wave. Well, yeah, if you're out here, you could. As this wave approaches shore, once this, if we're going to keep this at 5 feet, once it starts feeling bottom, this bottom part of the wave slows down. The top part keeps going according to Newton's first law of motion, and eventually it outruns the bottom, and then gravity takes over, and the waves will break. But you got to remember that whole idea of that 1/2. And you get this area here in the surf zone where you get the surf, hence the term surfboards. We looked at ocean currents. A couple things to remember. You got to make sure you know your reference point. Are we referencing an ocean basin like the Atlantic Ocean, or are we referencing a continent? So if we reference an ocean basin, we have warm currents on the west side of the ocean basins. Here we got one of the Gulf Stream, and this actually goes all the way up to England, Great Britain, and affects their climate, making it warmer. And then on the east side, we would have more of a cold water current. Now, if we're referencing the continent, the east side of the continent's the warm current, the west side is the cold currents. And we talked about warm currents come out equatorial regions and move towards the polar regions. Rip and longshore currents. Well, let's take a look at the rip current. Rip currents, really, it's a funneling of the water that strikes the beach into a narrow opening. And you can, this is a pretty good picture of one here, and you can see it's fairly narrow, but it dies out fairly, not far offshore. So two ways to escape a rip current: either just let it take you right out and then swim off to the side, or swim off to the side immediately. Do not swim against it. That's where people panic and they try to get back the quickest way, which looks the quickest way, but then they actually end up, you know, could actually end up drowning there. Longshore current. If you've ever been floating in Lake Michigan or anything, on an inner tube or something, you just started knowing yourself, drifting along the shore. It's because when the waves hit the shoreline and then the water bounces back, what you have is just everything start moving down, what's called downstream or along the shore. Hence the term a longshore current. So if you're out here, after a while, you're just going to start floating along the shore. The next one, a few of the terms we did with our hydrology project. Turbidity is really how cloudy the water is. It's got all these particles of mud and dirt and so forth. And when we were out there doing our testing, it was pretty turbid. You could not see very far into the water. Discharge is what you actually calculated. Things that would increase the discharge, as we noticed, rain would increase discharge rate. Melting of snow would increase the discharge rate. Anytime you can add, any type of water to a stream, it's going to increase the discharge rate. The particles themselves have really no effect on the discharge rate. It's got to be an increase in water. Melt off, runoff, increase in rain. Melt off, I mean the snow melting in the spring and so forth. We also looked at the headwaters of Mill Creek, which is up Cranberry Lake up by Conklin. Headwaters really kind of three things it can be. It's the furthest place in that river or stream from another one. So the headwaters, Cranberry Lake, would be the furthest place where the Mill Creek empties out, which is the Grand River. Typically at the headwaters you have the steepest slope. It doesn't have a chance to cut down yet. And as we also found when we looked at the relief of Mill Creek, it also has the highest elevation. If I remember right, Cranberry Lake was 723 feet above sea level, and then when it got down to the Grand River, it was 690, 680-ish, and so it's moving downstream. So, anyways, hopefully this will help. These are, again, the test is 35 multiple choice questions, and hopefully if you got any questions off this, feel free to ask, but hopefully this will help you out.